For the last 15 years, every major automotive executive in Detroit, Munich, and Austin shared the exact same hidden nightmare. It was not about battery cells, charging networks, or autonomous driving software. It was about a tiny, heavy block of metal hiding deep inside the electric motor. That component is a rare earth permanent magnet. Usually made from neodymium, iron, and boron, it is the invisible heart of the modern electric vehicle. It is what allows a Tesla Model 3 to launch from 0 to 60 miles per hour in 3 seconds without burning a single drop of gasoline. It gives electric motors their intense power, lightweight design, and long-range efficiency. There was only one massive problem. China controlled over 90% of the world's rare earth magnet processing. Every single time Tesla, Ford, or General Motors built an electric car, they were relying on a supply chain that ran straight through Chinese refineries. Washington spent billions of dollars trying to dig new mines in California and Australia, desperately trying to break that absolute monopoly. Then, Chinese researchers did something nobody in the West saw coming. They did not try to hoard more rare earths. They did not try to corner the market on neodymium. Instead, they invented a brand new, high-performance permanent magnet that uses absolutely zero rare earths. It relies on abundant, cheap materials like iron and ferrite, restructured at a microscopic level to deliver 95% of the torque performance of a traditional neodymium magnet at a tiny fraction of the cost. When the first prototype motor cleared laboratory testing, it did not just pass. It proved that high-performance electric vehicles could be mass-produced without touching a single grain of rare earth material. In a single move, the multi-billion-dollar rare earth bottleneck was bypassed. To understand why this invention sent shockwaves through Detroit and Silicon Valley, you have to look at the tiny component sitting inside every high-performance electric vehicle and the dangerous trap the entire Western auto industry built for itself over the last 20 years. To understand why a rare earth-free magnet is such a massive deal, you have to look under the hood of a modern electric car. When you step on the gas pedal, or the accelerator, in a traditional Tesla Model 3 or Model Y, electricity flows from the battery into the motor. Inside that motor, magnetic fields push against each other to spin the drive shaft. The stronger those magnets are, the smaller and lighter the motor can be. Back in the early days of electric vehicles, engineers tested all kinds of magnets. They tried basic iron magnets, but they were far too weak and heavy. They tried ceramic magnets, but they lacked the raw torque needed to move a 2-ton vehicle up a steep hill at highway speeds. Then came neodymium iron boron magnets, often called NdFeB magnets. They were a total miracle of modern physics. They created incredibly powerful magnetic fields in tiny, lightweight packages. Suddenly, car companies could build electric motors that fit inside a backpack while generating hundreds of horsepower. Every top automaker jumped on board. Tesla, Ford, General Motors, Volkswagen, and Hyundai all built their core electric vehicle platforms around neodymium permanent magnets. But that miracle came with a massive hidden trap. Extracting neodymium from the ground is dirty, difficult, and expensive. Refining it into ultra-pure metal requires highly toxic chemical processes that most Western nations pushed away decades ago due to strict environmental laws. China saw the opportunity that the rest of the world ignored. Over 30 years, Chinese companies built up the chemical plants, refining facilities, and specialized foundries needed to process raw rare earths into usable magnets. By the time Western car companies realized what was happening, China owned the entire chain, from the dirt in the ground to the finished magnet inside the motor. Tesla knew this was a massive risk. Elon Musk even publicly announced in 2023 that Tesla was working on a next-generation motor that would eliminate rare earths entirely. Tesla wanted to break free from the Chinese supply chain before trade tensions or export controls locked them out. For years, Western engineers insisted that building a light, powerful EV motor without rare earths was basically impossible without sacrificing range or speed. Then, a team of Chinese scientists decided to prove them dead wrong. For decades, material science textbooks said the same thing. If you take away rare earths, you lose magnetic strength. It seemed like a hard law of physics. If you used standard iron or ferrite magnets, your electric motor had to be huge, heavy, and inefficient. If you made the motor smaller, the car would accelerate like a golf cart and drain its battery in a matter of minutes. To break that law, Chinese engineers did not look for new exotic elements on the periodic table. They looked at common, dirt-cheap materials, specifically iron, nitrogen, and advanced ferrite alloys, and decided to re-engineer them at the microscopic level. The secret lies in a process called nanostructured grain alignment. Think of a standard magnet like a room filled with millions of tiny compass needles pointing in slightly random directions. Because they are not perfectly aligned, they push against each other, weakening the overall magnetic field. By using advanced heat treatments, atomic layer manipulation, and precision pressure casting, Chinese researchers managed to force every single microscopic grain inside the iron alloy into perfect, parallel alignment. They created an ultra-dense magnetic structure where every single atom works together to pull in the exact same direction. When they tested the prototype material on a lab bench, the results blew away standard industry models. The new rare earth-free magnet generated 95% of the magnetic energy density of a standard neodymium magnet, but it was made entirely from cheap, widely available raw materials that can be sourced in almost any country on Earth. Even better, it solved a major weakness that neodymium magnets have always suffered from: heat degradation. Traditional rare earth magnets lose their magnetic power when they get too hot. To keep them working under heavy acceleration, car companies had to add expensive dysprosium and terbium, two even rarer elements, or build complex liquid cooling systems around the motor. This new iron-based magnet, however, handles high temperatures with ease. It stays cool, maintains its pull, and operates efficiently under extreme strain. It was not just a victory in a lab. When engineers placed the new magnet into a full-scale electric vehicle powertrain prototype, the vehicle delivered immediate torque, sharp acceleration, and steady highway range, all without a single milligram of neodymium under the chassis. When those test numbers reached legacy automakers, engineers in Detroit and Germany realized the game had completely changed. In the automotive business, raw technical achievements mean nothing unless the financial math works. If a breakthrough is brilliant but expensive, it stays locked away in a laboratory prototype. But if a breakthrough makes a product both better and significantly cheaper, it sweeps through the entire market like wildfire. That is precisely why this new magnet architecture is sending shockwaves straight into the boardrooms of Ford, General Motors, and Stellantis. To understand the economic disruption, you have to look at how much an electric vehicle motor actually costs to build. In a standard high-performance EV, the permanent magnets inside the motor can account for up to 30 to 40% of the total motor cost. Neodymium prices are volatile. They swing wildly based on trade policies, mining quotas, and geopolitical tensions. When rare earth prices spike, the manufacturing cost of every single electric truck and sedan on an American assembly line spikes right along with them. By replacing neodymium with abundant iron and ferrite alloys, Chinese manufacturers can slash the raw material cost of the magnet assembly by up to 80%. Translate that into consumer terms. Removing rare earths immediately strips hundreds, sometimes thousands of dollars out of the base manufacturing cost of every electric drive unit. For American buyers sitting on the fence about buying an EV, this hits right where it matters most: the sticker price at the dealership. For years, everyday American drivers have pointed to high purchase prices as the #1 reason they stick with gas-powered cars. Automakers claimed they could not drop prices without losing money on every sale, largely because raw materials like lithium and neodymium kept baseline production costs sky high. China's rare earth-free magnet breaks that cost floor. It allows Chinese car companies to build light, punchy, reliable electric motors for a fraction of what Detroit pays. That means Chinese manufacturers can export ultra-affordable vehicles to South America, Southeast Asia, and Europe at prices Western brands simply cannot match without taking heavy financial losses. Even if Washington protects the U.S. domestic market with steep tariffs, American car companies operating globally will find themselves competing against foreign EVs equipped with far cheaper, highly efficient, non-rare earth drive systems. And that brings us to the midpoint of our story. Because this breakthrough isn't just about the cars rolling down American highways. It is about who controls the master switch of global high-tech manufacturing for the next 50 years. If you think this breakthrough only matters for family sedans and electric pickup trucks, you are missing the much bigger picture. Permanent magnets are not just for cars. They are the invisible muscle behind almost every automated machine on Earth. Take humanoid robotics, for example. Elon Musk has repeatedly stated that Tesla's Optimus robot will eventually be worth more to the company than its entire automotive division. But to make a humanoid robot walk, run, and lift objects smoothly, you need dozens of tiny, incredibly powerful electric actuators packed into its joints. Every single finger, elbow, and knee joint requires a compact, high-torque motor. If those motors rely on expensive neodymium magnets, building millions of affordable helper robots becomes an economic impossibility. By utilizing ultra-cheap, rare earth-free magnets, Chinese robotics companies can mass-produce humanoid workers at a fraction of the cost, flooding factories, warehouses, and homes with affordable, automated labor. Then look at renewable energy. Modern offshore wind turbines are massive engineering marvels with blades longer than a football field. The generators inside those giant ocean turbines use tons of rare earth permanent magnets to turn ocean breezes into stable power for electrical grids. When rare earths are expensive, building new wind farms becomes a risky, high-cost investment. Replacing those giant magnets with low-cost iron ferrite alternatives slashes the upfront price of clean energy generation across entire nations. And then there is the defense sector. Advanced radar systems, guided missile fins, military drones, and naval propulsion systems all depend on reliable, high-performance magnets. For decades, the U.S. Pentagon raised red flags about the fact that American military hardware relied on rare earth supply chains controlled by a geopolitical rival. The U.S. government spent hundreds of millions of dollars trying to secure domestic supplies just to protect defense manufacturing. China's material science breakthrough effectively flips that script on its head. While the West spent years worrying about securing legacy rare earth mines, Chinese engineers altered the underlying technology, making the mined minerals far less critical to industrial dominance. Which raises an uncomfortable question for Washington and Silicon Valley. How did the United States spend billions fighting the last supply chain war while missing the fundamental tech shift entirely? And more importantly, can Detroit and American tech firms adapt before it is too late? For the past decade, Washington's strategy to secure the green energy supply chain followed a simple, straightforward playbook. Copy what China did 20 years ago. Under massive federal funding bills like the Inflation Reduction Act, the U.S. government threw billions of dollars in subsidies at mining startups, refining plants, and processing facilities. The goal was clear: dig rare earths out of rocks in California, ship them to domestic processors, and build American-made neodymium magnets for American-made electric cars. It was an expensive, slow, and brutal effort. Building a modern rare earth refinery in North America takes nearly 10 years. It requires clearing endless environmental permits, constructing complex chemical processing facilities, and training a specialized workforce from scratch. Yet, while Western policymakers were celebrating the opening of a few domestic processing pilot plants, the underlying target post was quietly moved. American strategy was locked into securing 1990s-era magnetic chemistry, while Chinese material scientists were already developing the next-generation physics that made those refined minerals obsolete. Now, Detroit and Washington find themselves stuck in a classic innovator's dilemma. Should U.S. automakers continue investing billions into securing old-style rare earth supply chains just to ensure short-term motor production? Or should they abandon those projects midstream and rush to reinvent their entire motor manufacturing strategy around non-rare earth magnet physics? If American automakers choose to stick with traditional neodymium magnets, their electric cars will remain structurally more expensive to produce than global competitors. They will be forced to charge higher prices at home while losing market share in neutral international markets like South America, Asia, and the Middle East. If they decide to pivot to rare earth-free magnets right now, they face another massive problem. Chinese research teams hold the key patents, manufacturing processes, and specialized gigacasting techniques for these advanced iron ferrite alloys. American engineers will have to work overtime to reverse engineer, license, or innovate around China's new intellectual property just to keep up. It is a complete role reversal. For decades, Western companies held the advanced patents while foreign firms scrambled to catch up. Now, in the very core technology that drives the clean energy transition, the table has completely turned. So where does this leave the average driver sitting in traffic in Los Angeles, Chicago, or Dallas? When you step back and look at the entire landscape, this breakthrough is about far more than just magnets, electric motors, or automotive competition. It marks a fundamental shift in how global power, technology, and manufacturing will work for the next generation. For decades, the global economy operated on a simple rule. Whoever controls the critical raw materials controls the industry. Countries with oil reserves dominated 20th century energy. Countries with rare earth deposits dominated early 21st century clean technology. But China's rare earth-free magnet proves that material science can completely rewrite the rules of global competition. You do not always need to control the rarest resources on the planet if you can engineer superior physics out of common materials sitting right under your feet. For American drivers, this change will slowly show up in everyday life over the coming years. It means the electric vehicle you buy by the end of this decade will likely look, sound, and feel very different under the floorboards. The motors will be lighter, cheaper to build, and immune to global mineral trade wars. The sticker prices at dealerships will eventually drop, making long-range electric vehicles accessible to everyday families, not just wealthy tech early adopters. For Detroit and Silicon Valley, the lesson is stark and urgent. Relying on legacy manufacturing models, political tariffs, and old supply chain subsidies is no longer enough to maintain technological leadership. Winning the future requires constant, relentless innovation at the absolute edge of physics, material science, and manufacturing efficiency. The battle for the future of transportation was never going to be decided purely in policy meetings in Washington or corporate boardrooms in Detroit. It is being decided right now in material science laboratories, precision foundries, and automated assembly lines. China just proved that the single biggest choke point in green technology can be bypassed with clever engineering. Now, every automaker on Earth, from Tesla and Ford to Toyota and BMW, has to decide how to respond to a world where rare earths no longer set the rules. The race for the next generation of power is no longer about who digs the deepest mines. It is about who builds the smartest machines. Now, I want to hear from you. When you buy your next car, do you care whether the motor inside uses rare earth magnets from traditional supply chains? Or do you simply want the vehicle that offers the best range, performance, and price, regardless of where the technology was invented? Drop your thoughts in the comments below, hit that like button, and subscribe so you never miss our deep dives into the global tech shifts shaping our world. We will see you in the next video.